Hello and welcome to Padai on YouTube channel. This chapter is for class 10, chapter 10, light refraction and refraction. So in the previous time we have studied about the light, right? So we able to see things around us because of the light. Any object we could see is just the way reflected the lights that falls on it. Sun help us to see things around us during the day, and the night we use the source of light to see things. If any object is transparent, we could not see through, as the light allow them to pass it through. There are a number of common wonderful phenomena is associated with light, such as deformation of image, the twinkling of stars, beautiful colors of rainbow, and bending light. By observing the common optical phenomena around us, we may conclude that light seems to travel in a straight line. The fact that a small source of light casts a sharp shadow of an opaque object points to this straight line path of a light, usually indicated as a ray of light. So when anything that interrupt the light create a shadow. So in this chapter we shall study the phenomena of reflection and refractions of light using the straight line propagations of light. This basic concept will help us in the study of some of the optical phenomena in the nature. We shall try to understand in this chapter the reflection of light by spherical mirror and refraction of light and their application in a real life situations. So the main part of this chapter is, or the base 8, the light travels in a straight line. We are going to use this principle and to experiment various uh, mirror and types, reflections and refractions of light. Reflections. A highly polished surface, such as a mirror, reflect most of the light falling on it. You are already familiar with the law of reflections of light. Let us recall this law. The angle of incidence is equal to the angle of reflections, and the incident ray, the normal, to the mirror at the point of incidence, and the reflected rays all lies in the same plane. So these are the two laws, right, to form an image, or it is said about the reflection of light. The angle of incident is equal to the angle of reflection. So we will see that any light coming from the path as a straight light falls on any surface, and when it bounces back or when it reflects, it creates a same angle to its normal. The incident ray, the normal and the mirror, they are all lies on the same plane. These law of reflections are applicable to all types of reflecting surface, including spherical surface. You are familiar with the formation of image by plane mirror. What are the properties of image? Image formed by the plane mirror is always virtual and erect. The size of the image is equal to the object. The image formed is as far as behind the mirror as the object is in the front of it. Further, the image is laterally inverted. So these are the property of image created by the mirror. Now the curved surface of a shining spoon could be considered as a curved mirror. The most commonly used type of the curved mirror is the spherical mirror. The reflecting surface of a such mirror can be considered to form a part of a surface of a sphere. Such mirror whose reflecting surface are spherical or are round in a shape are called as spherical mirrors. We shall now study about a spherical mirror in some detail. So the plane mirror shows or create exact the image as it is. And if you go away from the plane mirror, it shows the same distance in the reflection. But here we are going to talk about the spherical mirror. Spherical mirror means a round in a shape, kind of a mirror, a part of a circle. The reflecting surface of a spherical mirror may be curved inwards or outwards. A spherical mirror whose reflecting surface is curved inward, that is, face towards the center of the sphere, is called a concave mirror. A spherical mirror whose reflecting surface is curved outward is called a convex mirror. So, on the base of the reflecting surface, they are divided into two types, concave and convex. The schematic representations of these mirrors is shown in this figure. You may now understand that the surface of the spoon curved inwards can be approximate to a concave mirror, and the surface of the spoon bulged outward can be approximated to convex mirror. Before we move further on the spherical mirrors, we need to recognize and understand the meaning of a few terms. These terms are commonly used in a discussion about the spherical mirror. The center of the reflecting surface of the spherical mirror is a point called a pole, right? So center point on the mirror is called a pole. It lies on the surface of the mirror and the pole is usually represented by the letter P. The reflecting surface of the spherical mirror forms a part of a sphere. So sphere means a circle. So this sphere has a center, and this point is called the center of curvature. If you just imagine a circle, and circle has a center, so that center is the center of curvature of the spherical mirror. It represented by the letter C. Please note that the center of curvature is not a part of mirror. It lies outside and its reflecting surface. The center of this curvature of a concave mirror lies in the front of it. However, it lies behind the mirror in case of it's a convex mirror. So you may have noted in the figure 10.2 A and B, the radius of a sphere of which the reflecting surface of the sphere mirror forms a part is called the radius of curvature of the mirror. It is represented by the letter R. So the distance between the center of curvature and to the pole is represented by the letter R. You may note that the distance PC is equal to the radius of curvature. Imagine a straight line passing through the pole and the center of curvature of the spherical mirror. This line is called a principal axis. Remember that the principal axis is normal to the mirror at this point or pole. Let us understand the important terms related to the mirrors through an activity. So if you draw a line from center of curvature to the pole, this line is known as a principal axis. Now take the paper at the first begin to burn, producing a smoke. Eventually you may catch the fire. For using the what they are talking about is the you use sunlight and a mirror effect, right, to by concave mirror to create a sun rays at a particular point, and that could burn the paper. Eventually it may catch the fire. So things get fire because sun converge the whole rays at a one point, and that bright spot by the mirror this spot of light is image of the sun on the sheet of paper. This point is focus on of the concave mirror. The heat produced due to the concentration of sunlight ignites the paper, and the distance of this image from the position of the mirror gives the approximate value of a focal length of the mirror. So it produces a huge amount of heat which is definitely a direct reflection of sun, making the burning or paper of paper. Let us try to understand this observation with the help of ray diagram. You see this figure 10.2, a number of rays parallel to the principal axis falling on the concave mirror. Observe the reflection, right? So they are all meeting intersecting at a point on the principal axis of the mirror. This point is called the principal focus or of the concave mirror. If you observe the figure B, the rays parallel to the principal axis are reflected by the convex mirror, but here the reflected rays appear coming from the point where the principal axis. This point is called the principal focus of the convex mirror. This principal focus represented by the letter F. The distance between the pole and the principal focus of the spherical mirror is called the focal length, and it is represented by the letter small f. The reflecting surface of a spherical mirror is by the large spherical. The surface then has a circular outline. The diameter of reflecting surface of a spherical mirror is called its aperture. Distance mn represented by the aperture. We shall consider in our discussion only such spherical mirror whose aperture is much smaller than its radius of curvature. Is there a relation between this radius of a curvature r and a focal length of a spherical mirror? For a spherical mirror of a small aperture, the radius of the curvature is found to be equal to the twice of focal length. So we can put in this way. So r is equal to 2f. This implies that this principal focus of the spherical mirror lies midway between the pole and center of curvature. This is the end of the first part. In the next part, we will learn about the image formation by a spherical mirror.